exam yet. I already gave you what I had. If the exam was written, it would have just been questions from the last time I did this, but then I gave that to you guys as practice exams, so I have to write a whole other one. Yeah, I haven't even started writing that exam.
We could help you. We could help you write the
You could, potentially.
Whole class, right?
Yeah, I mean, I definitely think I would be breaking some terms and conditions if I pulled up and showed any of you guys the test bank questions. I'm pretty sure I agreed to something when I got that, but like, I don't know. Turn off the camera. It can't hear me anyway. All right, well, here is, so your last exam included chapter 18, right?
Yes.
Wait,
No.
no, 17.
No.
17 is carboxylic acids. It included that one, but not carboxylic acid derivatives.
Correct.
Okay, so you got a ton to test over anyway. We're gonna see how far we get through this. And honestly, I think including the amount of chapter 21 that we get through anyway in the exam is gonna be good for you guys. Because I can very easily do lots of questions on this, or like a group of questions on this. And once you have this down, this is easy. So we talked about aromaticity yesterday, right? Wait, there we go. So aromatic compounds, they have some requirements. Here's the list. They have to be cyclic. They have to have a 2p orbital on every atom of the ring. And if it's an empty orbital or a lone pair, you can just decide that that's an p orbital. You need to be planar or nearly planar so that there's continuous overlap of all of those p orbitals. And you need, well, yeah, and it needs to be conjugated. I guess that's not on here. Although okay, I think you'd have a hard time having a planar ring that's not conjugated anyway.
If it weren't conjugated, it would be sp3. So you wouldn't.
Yeah, you wouldn't, okay, yeah. But I mean, it's a nice thing to say it should be conjugated because it's much easier to look at it and decide, oh yeah, that's conjugated every other, rather than like, does everything have a 2p orbital? What? So yeah, it needs to be conjugated. And then the pi electrons in a closed loop, so within the ring, we need to have 4n plus 2 pi electrons, which basically means we can't have a multiple of 4 pi electrons, right? And it can't be a radical, but like, radicals are never extra stable, and aromatic compounds, extra stable, right? Like conjugation a little bit extra stable, aromatic, hella extra stable. So basically it can't be a multiple of 4 electrons. What happens when we have all of these criteria are met, but we have 4n electrons? Like that square. Cyclobutadiene. So that covers, it checks all the boxes except it's got 4n pi electrons. And we actually call that anti-aromatic. Unlike aromatic, which are unusually stable, anti-aromatic, it's like almost made it to aromatic, almost made it to this unusually stable thing, and yet it's unusually unstable, like less stable than it should be. So it's weird. Yeah, cyclobutadiene only stable below negative 100 degrees Celsius. So yeah, like most of these anti-aromatic compounds are things that, unless you're specifically trying to study anti-aromatic compounds, and therefore you're doing everything at very low temperatures and such, they don't really exist for the most part. At least you're not going to be able to like isolate them. Yeah.
So like that compound has a lot of what is that, angle angle strain because of the 90-degree angle?
It does.
So does that contribute to the instability, or is it like
So-
just the conjugation system?
So it is unusually unstable for what it is. So if you like calculate, you know, how stable should this be based on it's a 4-membered ring and there are 2 double bonds. Like if you calculate that, like yes, it should be unstable. And then this guy, even less stable than that. Like even less than it should be, which is weird. Like it's just because of this 4n pi electron, so it's anti-aromatic. Yeah, I don't actually know why. I want to say either I have known why before, and the answer is physical chemistry and math and stuff, or I still definitely don't know why, and it's computational and physical chemistry, and I bet Dimitri knows because he does computational stuff in our lab, but like, I don't know. So, we can play a game where I show you all sorts of rings and we go aromatic, anti-aromatic, or non-aromatic, because there is a third option, right? It could just fail one of the 4 criteria. In this case, this guy looks like it should be anti-aromatic. And, well, there's not really a way for you guys to know whether it's anti-aromatic or non-aromatic unless you can Google the shape of it, or unless I tell you the shape of it. But this guy actually lives like a tub. Let me move here we go. Swoosh up here. Yeah. There we go. Looks like that. It's a tub. They call it a tub. It's like a boat, but it's not pointy on the end, so I guess it's a tub. Yeah. So, cyclooctatriene, or cyclooctatetraene, there we go, exists. We can, like, isolate this, and we can throw it in an X-ray diffraction instrument, and we can get the structure, and the structure is not planar, which kind of makes sense because somebody was able to isolate it in the first place. So, I don't know. To me, that kind of makes sense. But yeah, so this pi system is just not conjugated because you've got p orbitals here, but then these p orbitals are like here. And they're not parallel enough to really do the pi overlapping thing, right? So, yeah, it's not continuous. You don't really have that overlap between the bonds, and so it escapes the, I don't know, fate of being anti-aromatic. So, aniline. This wild ass dude. And, 14 aniline and 18 aniline. So aniline is, I guess aniline is just what they call it. Yeah, when you've got, yeah, I guess aniline is just the generic name for it's benzene but bigger. But these guys are wild. Like you have to straight up have like a number, like 14 aniline, 18 aniline. Have you guys heard of crown ethers? Okay, yeah, it's the same kind of a naming thing, right? Like, we just sort of got to the point where we're like, okay, I guess crown ether, you could just keep making it bigger, stick a number on there and call it this. This is the family now. That's these guys. As long as cyclic hydrocarbon with a continuous alteration of single and double bonds. Okay, cyclooctatetraene, which is this guy. Okay, so they don't have to be, anilines don't have to be aromatic. Interesting. Since cyclobutadiene is also part of it. All right.
Isn't it because the middle isn't, you're missing your third bond in your conjugate system?
Where?
Like within each hexagon, you have the 2 H's, which would it would allow conjugation on the outside, but internally, is that potentially why it's not considered?
Oh, no, these guys are aromatic.
Oh,
Sorry, these guys are aromatic, it's just not all annulenes are. I was gonna say, oh, maybe
Gotcha.
all annulenes are aromatic, but no, they make a point up here, cyclobutadiene and cyclooctatetraene. This guy in the square, the anti-aromatic
Gotcha. Okay.
boy,
I was
the square anti-aromatic boy, and the tub that's not either of them, they count as annulenes. Sorry, I was just trying to figure out if they were all aromatic. So, not all annulenes are aromatic, but all annulenes are this ring, and you've got a continuous alternating single and double bonds. So, they're all at least fair game for the question, is it aromatic, anti-aromatic, or not aromatic? So, 14 and 18 annuline are aromatic. They've got some nice resonance energy. 18 annuline is, 100 kcals per mole? That's kind of a lot. So, a fun thing is NMR. Do you guys remember where benzene hydrogens show up in NMR? So, I always draw it because you're always looking, like Spectre's pictures anyway, so I remember numbers when you can just remember approximately where-ish it is, right? So, 0 ppm, and I don't know, let's go up to like 10, even though almost nothing is up here because that's somewhat evenly spaced. Ish. Okay, so in NMR, you have like just your CH, like normal hydrocarbon things. They show up like way down here, right? Like below 2, probably even around, like if it's just CH bonds, they're way down here, right? If you have a hydrogen on a nitrogen or an oxygen, then it starts showing up kind of in the 4-ish range, in this kind of 3 to 4-ish range. Maybe there is a better cutoff for this. And then if you have a CH that's next to something, then you start pushing more that way. Let me do a downfield, upfield thing real quick, because downfield, upfield. Give me the picture. And never remember which direction is which.
That was downfield.
That way's downfield? Okay. Downfield. Deshielded. Shielded. I also never remember which way is shielded or deshielded. So, basically, benzene shows up like right around 7. Which is really nice because, you know, it's just a nice, I don't know, it's way over there. Like, it's not ever mistakable. You have stuff that shows up in the, that might start a little too low. It's probably more like, might be something more like this. I don't know. It wasn't supposed to be that accurate. Around 7, in the general range of 7. I mean, if you're way up at 10, you've got something else going on. Carboxylic acid, probably. That's like the only thing I know that shows up at 10. If you've got negatives, you've got like metals and shit, usually. But this is kind of the normal stuff that's going on. plain stuff, CH stuff, CH next to or nearer to additional electron density, and then up right there in that middle, hydrogen's bonded to a nitrogen or an oxygen. If you see them, because if they're acidic enough, then they'll just exchange with deuterium. If you have a, what's it called? It's not a protonated solvent, it's a,
Deuterium solvent?
well, no, it's the word for it, if it's got a proton that it will let you, like, if it's got exchangeable hydrogens. You know what I mean? There's a word for that. Protic. Got there. Protic. Protic is just, are there hydrogens that, even if they're not like super acidic, they're going to be lost and like stay that way, as long as they're easy to detach and reattach, then your solvent is protic. And you can do the same thing with deuterium as protons, so if you have a protic solvent, your NHs and OHs tend to kind of disappear. Okay, so with these guys, the reason that benzene is way up here, way de-shielded, is that we get these ring currents going on with benzene. So basically, like, the electrons have a closed loop, and they just sort of go around, and when electrons move, you generate a magnetic field, right? Like physics stuff, you have electron current, you get magnetic field this way, and so we get a perpendicular magnetic field that's basically like, it ends up donut shaped, and it does like a weird like out and around thing. Basically, the result of that is that all of the hydrogens on the outside of any aromatic annuline like this, they are going to be way de-shielded and way down here. So benzene only has them on the outside because it's hasn't reached that level where it's big enough to have some on the inside and still be fine like this. But, so they're gonna be way up here. This guy, Jesus, 18 annuline, these guys are up at like 9.3. So I stand corrected. I guess other things are up here, but you'd be able to tell the difference because the carboxylic acid would, well, you could see it in IR, plus the NMR peaks. You never have any NMR peak connected to hydrogen or oxygen or something like that, like they get kind of broad, like round, and you'd be able to tell the difference. But yeah, these guys way up at 9.3. These guys on the inside, they get incredibly shielded just because of the direction, I think, in which the magnetic field goes. So if you have an annuline large enough to have hydrogens on the inside, these guys go wild, and these are at -3. So I guess you can get there without metals, but you can't get to the negatives without doing some wild ass shit, so, you know. But yeah, so, there we are. Okay, yeah. Characteristic of all compounds that meet the Huckel criteria for aromaticity. So if it's aromatic, it has that ring current, and you get this. You get these guys on the outside go way up, and these guys on the inside go like unreasonably down. Yeah. Let's see. This guy, 10 annuline, is non-aromatic, and then they figured out the reason is because, oh right, each of those have a hydrogen, and honestly, the hydrogens should be, well, like on top of each other, sort of. So it ends up kind of putting a kink in the ring like this, and so it's not planar. Which again, you would have no way of knowing unless I told you what the shape is. So when we play the aromatic, anti-aromatic, or non-aromatic game, if planarity is the problem, you'll have like a 3D image of it, or you'll like be told that it's not planar or something like that, right? The game will be mostly, do I have alternating double bonds, and do I have 4n or 4n plus 2? Yes.
On one of the previous slides,
Yes.
it had like hydrogens real close to each other.
Yeah, like these guys?
Yeah.
Yeah, they are nice and close to each other. So I think what we've got here is that, notice here they didn't actually draw them because like they're like one bond, like to make that nice little 6-membered ring, they're like right there, like almost like the hydrogen should almost be where this carbon is. And so then it's pushing it out even further. But so over here, where they seem really close together, they actually drew out the hydrogens. So like this to here, those are 2 bonds away, right? So these 2 hydrogens are close, but in this case, these 2 hydrogens, like hydrogen-carbon bonds are shorter than carbon-carbon bonds. So here we've got 2 instances where we've got hydrogens that kind of, if they were carbons, they'd be taking up the same spot. Because they're hydrogens, they're kind of smaller and it's fine. Over here, like where we want to draw the hydrogen is literally on top of this carbon, right? Because there's only one bond missing from this hexagon. So like one more bond goes down here. So it'd be like kind of on that. Does that make sense? Sort of, not so much?
So it's essentially 2 hydrogens in the space of 1 bond here, where it's 2 hydrogens in the space of 2 bonds.
Yes, yeah. 2 hydrogens in the space of 1 bond and 2 bonds, and there's a hole for an atom. And we've got, yeah. Does that make sense?
Yeah.
Okay, cool. But yeah, like I would, if the only problem is that it's not planar, you would have a 3D picture of it, or you would know or something. I don't know if I'll trust the 3D picture, we'll see. Not from your book at least, those are terrible. Okay, let's see. The ring of 10 annuline, let that guy, can assume a conformation close enough to planar that it becomes aromatic if the 2 hydrogen atoms facing inward toward the center of the ring are replaced by a CH2 group, which is real weird, because it's still not entirely planar, and one of these guys is sp3, but our Huckel criteria for aromaticity is just that everybody in the ring, a closed loop, right? So it can kind of be held together by other things, and it doesn't matter if that part is part of the conjugation. So we just need a closed loop of conjugation, right? Weird.